Okay, let's do this problem. A thin glass rod forms a semicircle of radius r equals 5 centimeters. Charge is uniformly distributed along the rod with plus q equal to 4.50 picocoulombs and minus q equal to negative 4.50 picocoulombs in the lower half. What is the electric field at P, the center of the semicircle? So this problem is about finding the electric field due to a continuous charge distribution. Now recall the strategy to finding the total electric field is to break up this continuous charge distribution into tiny little infinitesimally small point charges. So we would make this say dq, and then we would look at the contributions from all of these dq and integrate from here all the way down to here. Now we're gonna make a little use of the symmetry involved. If you notice, this little charge dq will make a small little electric field that points away, since it's assumed to be positive. That would be dE. Now a similar charge, but negative, exists down here. If you just do a mirror symmetry, that it goes straight down to here, and that will be minus dq. The electric field due to this will be towards the charge, but the same magnitude. So in the end, you'll have two arrows that point like this. Now notice from the symmetry that their vertical components will add, whereas their horizontal components will cancel. At the end of the day, you're going to have a total electric field that's only pointing downwards and is due to the sum of both of these arrows. So let's write down what this would be. We would have dE equal to, it's pointing down, so it's negative, and then it's made up of both of these, so there's going to be two of them, times dE in the y direction, since we're talking about the vertical component being in the y direction. Now, this consists of a magnitude times a sine or a cosine. So the magnitude, say we're looking at the plus dq, the magnitude is from Coulomb field, which is k dq over the distance squared. In this case, it's r squared. Then we have to multiply by a sine or cosine because we want just the vertical component. So if we call this theta, then we're interested in this component right here. The vertical component is adjacent to theta, which means it's going to be cosine theta. Okay? So this is the infinitesimal amount of electric field due to both of these charges, the plus dq and the minus dq. To get the total electric field, we just want to integrate this. So the total electric field is going to equal the integral of dE is equal to the integral of minus 2k dq over r squared cosine theta. Before we can integrate such a thing, we'd like to remove all the things that are constant and only keep the things that change. Remember, we're changing this where the position of where this dq is, going from the top all the way to the bottom. So the things that are constant obviously will be minus 2k. R here is also constant. Usually it's not, but in this case it is because the radius doesn't change as you vary it. So it's going to be over r squared. And then we leave what's left is cosine theta and dq. Okay. Now theta is not constant because this angle theta is the thing you're going to vary. So if this is theta, then what's up here is also theta. And that's what we're going to change as we go from here down to here. Theta will go from 0 to 90 degrees. Now, as is, we can't do this integral because we have two variables that are changing theta and q, and we need to make them only one variable. So we have to find a way to write theta in terms of q or q in terms of theta. And we can do that because it's a uniform charge distribution. The amount of charge that is spread out here must be the same density as the amount of charge that's spread along this whole thing, right? So the ratio, say, for example, dq to this small infinitesimal distance, let's call this small infinitesimal distance ds for arc length, then the ratio of dq to ds must equal the ratio of the total charge plus q over the total distance from here to here. And if you can tell that this is a quarter of a circumference. The circumference is 2 pi r over 4. And look, simplify this, and you'll get 2q over pi r. Now, what is ds? If you recall, ds is the arc length, and in polar coordinates, it's going to be equal to r d theta. So what we have then is dq over r d theta equal to 2q over pi r. The r's will cancel, and you'll then have an expression for dq that equals dq equals to 2q times d theta over pi. So now we're going to take this expression for dq and plug it in for over here. Okay, so let's do that. We're going to have electric field equal minus 2k over r squared, the integral of cosine theta 2q over pi d theta. Again, we take out terms that are constant, so we'll have minus 4k q over pi r squared. And we're left with cosine theta d theta. Now, what are the limits of integration? It's going to be 0 to 90 degrees or pi over 2. Now, why didn't we go all the way from why isn't it from 0 to 180? Remember that we broke it up into 2. We already counted for the negative part. So they with this factor of 2, right? So we already counted for the charge on the lower half. So the limits are just going to be from 0 to 90 or pi over 2. Okay, so this integral is easy to do. The integral of cosine theta is just sine theta. And we're going to have then equal to minus 4kq over pi r squared. Sine theta evaluated from 0 to pi over 2. Sine of 90 degrees is 1, and sine of 0 is going to be 0. So this answer will be minus 4kq over pi r squared. And we can put in the numbers and see what we get. We have minus 4, 8.99 times 10 to the 9 times the charge, which is 4.50 picocoulombs, 10 to minus 12 coulombs, over 5 centimeters, which we have to write in meters, 0.05, and squared. Okay, when you put in all these numbers, what we'll get is minus 20.6 newtons per coulomb. We'll box our answer.